In system identification, we all know that the very first step is to use our prior knowledge to define a model class to be identified. So in this video clip, I would like to just review in short a background in linear system you should know for system identification purpose. In this class, we're going to deal only with linear system, linear time invariant system. So if we categorize into continuous time and discrete times, so let's take a look at the form of continuous time linear state space model. For autonomous system, which means the system that can run independently by itself, there is no input. Okay, the system description is x dot equals a xt, y equals c xt. Okay. And the system with input, of course, you have the term but and dut in the state equation and the output equation. Please review that we call the matrix A the dynamic matrix because the matrix A is very important that it defines the dynamics of the system. You should all know, I think we're going to talk in the next slide that the solution of the continuous time linear system will highly involved with the state transition matrix E to the AT. And what we learned before is that the eigenvalues of A define the mode of the system, define how the system, how fast the system decay. The system is stable or unstable. It all depends on the eigenvalue of A. And that's why A is called the dynamic matrix. The matrix B is called the input matrix because it suggests the gain from input to the state equation. The matrix D at the same time is called the direct forward term because the equation of the output itself, y depends on the state x, and it has a direct addition term from u. Okay, we call the matrix C the output matrix because it's explained the gain from the state variable to the output y. Everything is vector. Okay, we have a usual notation that n define the number of state variables, and that define the order of the system. Okay, you could have multiple output, y is a vector of Rm. You can have multiple input, u is a vector of Rp. Please review that for state space equation for autonomous system, is all require the matrix exponential e to the at. In terms of linear system theory, we use the term state transition. But as in mathematics, this is called matrix exponential. Okay. This matrix exponential can be computed analytically, either by using diagonalization technique if the matrix A is diagonalizable. I think you should review that all the entries in the e to the at is a function of e to the lambda t, where lambda is the eigenvalues of A. Okay, so we all know that e to the lambda t is decaying if the real part of lambda is negative, right? E to the lambda t go increasing if, of course, if real part of lambda is positive. And that's why we say that the eigenvalues of A indicate the stability of the system. if you're not in control before, you should know that when we say about stability of the system, what does it mean? Napat, can you answer that? The system is stable if the response.
If as t is it convert to infinity, the yt will convert to constant value.
Okay. Yes, you say that, but let me just say that, okay, we can adjust so that we can say the state variable convert to 0 as, oh sorry, not infinity. The state variable convert to 0 as t goes to infinity, as long as your input u is bounded. Okay, when you say it convert to a constant, we can adjust the coordinate that you kind of make a cheaper variable, right? If xt go to a constant, it means that in another coordinate that you just transform like this, your x2d go to 0. So in system theory, we would use the term that the state variable go to 0 if the system is stable. Okay. When the system has input, the response comes from two terms. I would like you to review and verify the expression of this. This is from linear system class again. The first term depends on the initial condition. The second term comes from the second term comes from the convolution between state transition matrix and the input u. Okay. And then the output, of course, is just to multiply c to the whole term. The main point is that your state variable response, okay, has the 0 input response and 0 state response. Which one is which? 0 state response is this one. 0 input response is this one. It's called 0 input response because it's a response in the condition that there is no input. Okay, it is called 0 state response because this is the part you would see when the initial state is 0. Okay, there's some analysis in between, but I think we all know. Who's taking linear system 2432? Did you take the course? Are you taking this course? Linear control system 2. City Park, are you taking this?
Yes, I have taken last term.
Yes, okay. You see that we have all of these, right? Take the Laplace transform, right? Si minus a xs equals a xs plus bus, and then you solve the equation using inverse Laplace transform.
Yeah.
Okay, yes, please review. Okay, Napat. Now let's talk about discrete time system. The discrete time system is in this format for autonomous and the system with input. Okay. And then the response. So luckily, the response of a discrete time system can be solved more easily compared to the continuous one because you can just iterate the equations. Okay, but in the discrete time, the state equation, the state transition matrix is A to the T. Again, the way you solve it is just, if you don't need anything else, you just, okay, I can just write x1 equals x1 equals a x0 plus b u0, and then you write x2, just like recursively write the equation, and then just plug in the response of x1 from the first equation. Can you do this at your own time? Okay, just keep writing this, and then you will see that the closed form solution is given by this. But it still contains the same concept, which is the response of xt contains two terms. The red term is called what? Between zero input and zero input response and zero state response. The red term is called ping.
Yeah, Chan.
Mm.
Zero input response.
Yeah, this is called zero input response because it's given as if there was no input applied. What about the blue term, ping?
The blue one is zero state.
Zero state response, obviously. And if you look closely at the zero state response, this is the convolution term, right? Between the state transition matrix and the what? And the input convolution. Okay, please review. A model can be also given in the form of transfer function. Okay. Also, when you have a state space model, please review how to transform from state space to transfer function. Okay. Continuous time, we use S, the frequency domain variable. How do we get this? This is very simple. Just apply the Laplace transform. Okay. And for discrete time system, we just apply the Z transform. Apply the Laplace transform, City Park, real quick, to the very first equation. You would get
Si minus A of xs equal to bus.
yes, Si minus A xs equals bus. Because you just do it real quick, right? Actually, it's S xs. If you look at the term on the left, and minus what? Minus x0. Okay, but we assume it's zero at the moment as we derive the zero state response. Okay, and then on the right hand side you have AXS plus BUS, and that's why when you move around the equation you get this. And then for the output equation, can you just inverse first for the value of S that this operator defines, which is this is called resolvent operator or Si minus A inverse. So Y of S, Laplace of the output equation is
C Si minus A inverse and B plus B.
Oh, yes, you do it too quickly. I was just about how to get to this step by step, right? So it's going to be, this is from output equation first, and you just plug in xs from here. C Si minus A inverse B plus D times US. The transfer function, please review in control. The transfer function, as the name suggests, transfer. It transfers the effect from U to Y, right? Okay. In a scalar, if everything is scalar, we common use the the quotient between Y and S to define transfer function. But that doesn't hold anymore when you deal with MIMO. So we often use this notation instead. Y equals HU. Okay, H transfer the effect from U to Y. And for the discrete time system, we do the same, just apply the Z transform. Okay, and recall that the transfer function h, if you take the inverse Laplace transform, we call it impulse response. Because what? Because it's the impulse response, because if u is the impulse response, if ut is delta function, Laplace transform is Ping. What is the Laplace transform of impulse?
Should be 1.
1. Okay, so 1. So that means your output response is actually the same as the inverse Laplace transform of your transfer function. So in that case, it is called impulse response. Okay, so to review this, okay, please review the concept of stability. Okay, and there might be the time we mentioned about controllability and observability. Controllability is ability of the system where it allows you to choose arbitrary input to move the target state to be anywhere on the Rn space. This property can be explained from A and B only. For observability, which is going to be more relevant to our system identification or the model estimation process, is the ability how you can get back to the initial condition from the measurement Y. So this is a property you can infer or explain from A and Z only. Okay. I think this is all basic knowledge you should review for linear control system. You have questions?